Okay, this is problem 6.4, sample problem 6.4. Calculate the wavelength in nanometers of the photon emitted when an electron transitions from the n equals 4 state to the n equals 2 state in a hydrogen atom, okay? So this is the Bohr model at work. We're looking at different energy levels. So I'm going to show the two of the relevant levels here. So this would be n equals 4, n equals 3, n equals 2, n equals 1. So what we're looking at is the electron undergoing a transition from 4 to 2. It's starting off at 4, so n initial is 4, and it's ending at 2, so n final is 2. Okay? Now, there are different approaches to this, but I'm going to show you probably the simplest one based on your textbook, and that is 1 divided by wavelength is equal to 2.18 times 10 to the minus 18 joules over Hc times 1 over n final squared minus 1 over n initial squared. Now, I'm going to go show you something. If you take 2.18 times 10 to the minus 18 joules and divide that by Hc, H is Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds, and then you take c, which is the speed of light, 2.9979 times 10 to the 8th meters per second, and you do the division. You do this constant 2.18 times 10 to the minus 18 joules over Hc. What you get is the Rydberg constant. So I'm just going to go ahead and write this to 4 sig figs. 1.097 times 10 to the 7th. Reciprocal meters, 1 over meters, times 1 over n final squared minus 1 over n initial squared. Okay? Now, 1 over 2 squared is 1 over 4. And 1 over 4 squared is 1 over 16. So what you have in the parentheses is 1/4 minus 1/16. Well, 1/4 is the same as 4/16. 4/16 minus 1/16 is 3/16. Okay? So 1.097 times 10 to the 7 reciprocal meters, and that would give you 1 over wavelength, okay? So all we got to do is that arithmetic, and that'll give us 1 over wavelength, okay? So 1.097 times 10 to the 7th, there's a big number, that's the Rydberg constant, times 3 divided by 16. And you get 2.057 times 10 to the 6th. Again, reciprocal meters. Now, keep in mind the n values are unitless, so they're not going to affect the units. But we don't want to know 1 over wavelength, we want to know wavelength, so we got to take the reciprocal of it. So 1 over lambda is just lambda, so we got to take the reciprocal of both sides. So 1 over 2.057 times 10 to the 6 reciprocal meters. Now, luckily, our calculator probably still has that number in it. There it is right there. So let's just take the reciprocal of it. And there we go. 4.86 times 10 to the minus 7. And that would be in meters now, right? Because we're taking the reciprocal of 1 over meters, which would just be meters. Now, the question asks for nanometers, so let's do the conversion. 1 nanometer is 1 times 10 to the minus 9 meters. So if we have 4.86 times 10 to the minus 7 meters, and we're going to multiply that by 1 nanometer divided by 1 times 10 to the minus 9 meters, meters cancel, and you'll get 486. You get 4.86 times 10 to the 2. That's 486 nanometers, or 4.86 times 10 to the 2 nanometers. And if you go back to the original chart of the hydrogen spectrum. We call this the Balmer series. And the Balmer series is the one that's in visible light, that has visible light, visible range. And so what happens is, if it's n equals 3 goes to n equals 2, that's 656 nanometers. And if it's n equals 4 goes to n equals 2, it's 486 nanometers. So right there, that tells us what's going on here. And then n equals 5 to n equals 2, that is 434 nanometers. I'm just doing this from memory. And then n equals 6 to n equals 2 is 410 nanometers. So the 486 nanometer, that one right there, that's what we just got there, right? That is the case, that's the line that you're going to get for the hydrogen atom if the electron goes from the 4th level to the 2nd level, which is part of the Balmer series.